Okay, I'm gonna start recording, so don't say anything embarrassing.
I'll try.
And I assume you're gonna share the screen and stuff?
Yeah, I will share.
Okay, great. So let's.
Okay, I'm gonna start recording, so don't say anything.
Oh, whoops, sorry. All right. Okay, without further ado, it's really a huge honor and pleasure for us to have Igor Gilitschenski come and talk at our reading group. I've known Igor for a long time from our work together at MIT. In fact, Igor kind of took over the lab position that I held at MIT when I left, and took the project to much higher heights and much greater success than I was ever able to. And now he has accepted a position at University of Toronto. That's a public thing, I think. And we'll be starting there next September. And so he has, I mean, it's almost easier to talk about what Igor hasn't done rather than talk about what he has done. But suffice to say, a large breadth of work from robotics perception to control, and a diversity of robotics platforms that Igor has worked on, from quadrotors to autonomous cars. And so without further ado, I will let Igor take it away. He's going to talk about context-based situational awareness for autonomous driving.
Yeah, thanks so much. That's too kind of an introduction. Can you guys see the slides, first of all?
Yeah.
The sharing work? Okay. Perfect. So yeah, thanks so much. It's a great pleasure to be here, and Liam was, as so often, way too humble about his huge and amazing work. And a lot of what I will be talking about today would not be possible without the work that Liam did in actually building up our platforms, including the platform that you see here on the title slide. We have two of those, and it has been mainly built up by Liam, and allows us now to do a bunch of very exciting experiments. My usual start when I talk about autonomous driving is one of my favorite TV shows from when I was a kid, having a car and combined with a computer. That was amazing. I liked it more for the computer. My father was always more excited about cars. He was kind of sad that I don't like cars as much, and I was like, why would you need cars if you can have computers? It's much more fun. So that I work now on cars and still do CS, I think makes him proud and me happy. So I optimized not on purpose for this. Okay, I think here I don't need to motivate it as much. As you know, autonomous driving is hard. Companies are actually deploying a lot of autonomous or semi-autonomous products, such as parking, and it is, as you know, like a very challenging thing to do. Driving at high speeds is not only hard, but if it goes wrong, it's very dangerous, and that's basically, to some extent, it's one of the reasons why we can feel safe about our jobs, because there is still a lot of research to be done in order to make all of this work robust and stable. I want to talk today about 4 topics. The first one I wanted to do faster because it involves some work we did with Liam together, but I see here some people here who probably don't know about it. So maybe if you have more questions, we go into detail about some classical model-based approaches to driving. And as announced in the abstract, what I want to talk about today is how a lot of the deep learning approaches are now inspired one way or the other by initially some earlier model-based approaches. So what I mean by that is basically when I started doing deep learning, it was just you have some component of a pipeline, or you have even your entire driving stack, and you simply try to replace it by a very simple supervised learning problem with a very simple architecture, and you just need a good data set that tune some hyperparameters. And in the last years, like I would say last three to 5 years, we have seen the actual neural network modules themselves get more and more complex and drawing more and more inspiration from all classical approaches. And terms like differential programming came up, or you could say came up again, thinking of how to simply make classical pipelines differentiable and integrate them as part of neural network pipelines. And within this scope, I want to talk about some of the approaches that we were working on that drew inspiration one way or the other from some earlier work. So let's start with model-based approaches to driving. A lot of very hard driving tasks are still solved with relatively classical approaches where you have a very structured pipeline. So for example, if you want to drive in the countryside or on roads where there are not enough or too confusing features to localize, one approach that we were looking at, this was the work together with Liam, was the MapLight work. And in this work, we basically detected the road and used this information to register our car with an existing map. And the map was not like a SLAM map, like you know it, where you have some sort of 3D model, but the map was, in our case, OpenStreetMap. So the same type of maps that humans would use, a simple topometric map. If you take like a classical driving pipeline, we had only a slight modification that involved a learning-based segmentation module, but everything else was very clear, structured, and followed very, very like the typical approaches how you would design a driving style. And these approaches are very successful, and this type of approaches is still what is used today by most car companies. And what they end up doing is they take always one of these approaches that you see here and replace it maybe by some neural network module. But basically, no, in practice, we're not there, not at a point yet where we're doing things like end-to-end driving in any commercial application. It's mainly a research topic. Similar, like you can even push these to the extremes. So here you see us basically navigating with this classical approach with MapLight. But if you do it right, it like drives very robustly. Many like SLAM systems might have a very hard time, particularly recognizing this place in winter. We have to recreate our maps because nothing looks the same. But for an approach that simply looks at the road and tries to recognize the road structure and co-register it, it's very robust. A lot of the advances that we have seen in these classical approaches are also due to use of better sensors. So here, no matter what approach you use, you will have a very hard time recognizing anything or navigating anywhere. So the LiDARs might have a hard time, cameras will have a hard time. But what you can in the end do is use a novel sensor type, and you don't need any learning at all. So in this work, we looked at using a ground penetrating radar. And this project actually also started back when Liam was still at our lab. The exciting thing about this new sensor is it is, of course, not useful for things such as collision avoidance because it looks under the ground and not around the car. But for navigation in as bad weather as you can imagine, this sensor allows for the robust navigation by looking at subsurface features. So this is a top-down view of the sensor. It uses a GPS, additionally to the ground radar, it uses a GPS for getting a rough localization estimate, and then it creates a subsurface map that looks a little bit somewhat like this. So it measures the strength of reflections in relation to depth. And the cool thing about using a sensor like this is it allows, even like with a relatively simple approach such as scan matching, this sensor allows to drive robustly in New England winter conditions. So here we're driving again at our test site, and The exciting thing about this is that this map was, I think, recorded even in summer, like under a completely different weather conditions. So something that is almost unthinkable for classical SLAM approaches, even if it's raining or if there is a snowstorm. As long as the car can localize, can drive slow enough to detect potential obstacles that are nearby, a sensor such as the ground penetrating radar would provide sufficient detail about the environment to actually robustly localize and to stay on the road, even if the road is full of snow. And this is to us exciting because that's actually the type of condition that humans can drive in. And if we want to solve like the edge cases of autonomous driving, particularly on country roads, this is one of the challenges that we need to face. And this, of course, is more an industry rumor, but the industry rumors are that also like several of the big players in the autonomous driving space now started looking at ground penetrating radars. And I think this has like a huge potential. So we had some of the first papers working on it. So, okay, so what I'm interested in is how can we draw inspiration from what we know about environment models, from what we know how to model cars, how to model maps, how to model uncertainty. How can we use this inspiration to develop better autonomy pipelines? And one approach that we use for end-to-end learning to drive is data-driven simulation. So in data-driven simulation, we are looking at the problem of deep learning-based control. So the problem of using neural networks to control a car. We're also looking at other robotic platforms. In this case, these were cars. And one problem of using neural networks to control cars is to obtain the right training data. Using training data from human drivers is very difficult because this training data either does not contain dangerous edge cases, or it may contain these cases, but in order to record these cases, you need an extremely experienced driver who would be able to drive in these dangerous situations and still successfully survive and successfully navigate. So our idea was to use real-world data and to develop a simulator that allows agents to autonomously navigate in an environment that is photorealistic and based on this real-world data. There is quite a bunch of interesting approaches of using simulation for driving tasks or for robotics. First of all, of course, model-based simulators, such as Carla, I think Zumo, which are very nice for using purely simulation-based research, but it's very difficult to use the simulators for actually transferring some sort of learned policies onto a real platform because there is no photorealism, so they are not photorealistic enough to do this. Another class of approaches is starting off with some sort of model-based simulators and then using domain transfer. So taking model-based simulator data as input and outputting them domain transfer data that looks photorealistic. This already enables some sort of transfer to the real world, but is still somewhat challenging. And it's very limited. It also lacks the same semantic complexity of the real world. And a somewhat recent line of research that is now becoming way more popular is data-driven simulation. So instead of using a simulator and then making it look as realistic as possible, you take some real-world data set and use this real-world data set to create a simulated environment. And this is exactly what we were looking at for driving. So our data set could be as simple as recording simply a trajectory on the highway. And within the simulation, we can have synthesize new viewpoints on this trajectory. And this synthesis would still look photorealistic enough to train driving policies. So for the training of the driving policies, we actually only use a subset of the, only a small fraction of the image, because neural networks are actually very, very strongly focused on things like lanes and lane markings. And we don't even need to use the full image. I was talking about how this is related and how what we do is related to classical models. And it's the same thing actually for the data-driven simulator. So the data-driven simulator enables a neural network to learn complex driving policies because it actually knows already a lot about the driving task. In that particular case, we actually gave the simulator information about the car's dynamics, and we use, although neural network-based, but not always neural network-based, depth estimation to actually obtain a 3D observation and synthesize new viewpoints. So even if the approaches that we use are not, are ultimately resulting in just a very plain-looking neural network, what is behind the scenes to train this neural network actually makes a lot of use of domain knowledge. In that case, in this particular case, the domain knowledge is knowledge about the dynamics of the car and knowledge about image formation from depth data. So the way the simulator works is basically we have a recorded data set, and we are located somewhere in the virtual world where we take the closest observation from this data set in our virtual location. We can reconstruct the depth of this observation, and we can use this depth to create a new synthetic observation. And this allows us for small disturbances or for slight repositioning of our vehicle, and allows us ultimately to drive in simulation. It doesn't allow us for things such as 180-degree turns, but for lane-stable driving, we don't need this type of freedom, at least for this simulator, we don't need it. And it not only allows us to simulate the driving task, but it also allows us to use things such as reinforcement learning for actually training a neural network how to drive. We use even very simple cost functions. So in this case, we use policy gradient, and as cost function, we simply use the deviation from the center line. And it's not because we were lazy. In fact, we have also tried to use more complicated cost functions, but it was more because we wanted to show that even with simple cost functions, we can learn how to drive. I think there was a question. I'm okay with questions now. Liam, what do you think?
Yeah.
Yeah,
Ray,
so
go ahead.
Ray, please.
Hi, Igor. This is Ray, VM student. I have a question more. I'm interested to know how you generate the simulated scenarios. Can you go back to the previous slide?
Yeah, sure.
So I read, sorry?
Yeah, yeah.
So I quickly read the paper, and then, so I guess if I understand correctly, the way you generate that is you train a model to predict the depth for each frame that's in your database, right? And then based on that, if you know the intrinsic parameters of your camera and the depth and the observations, then you can project that pixel to the 3D space. And then you keep doing it for all the frames in your database to build a 3D map, sort of.
You almost gave the full answer for me. So maybe two things to add to this. We also looked at doing this just with stereo cameras, so we don't always use depth prediction. But one approach was depth prediction. It worked with depth prediction as well, but stereo camera just gave a little bit more robust depth. We probably also didn't train long enough. And the second part of the answer is we don't even build a full map. We literally, for each virtual position, take the closest observation and just use this closest observation to synthesize the new viewpoint.
Oh, okay. So
there is not even a full map at the moment, at least.
Okay, so two questions then. So first is for each observations that you gain when you collect the trajectory,
Yeah.
do you also have the ground truth XYZ position or no?
Yeah, we have the ground truth position. We from GPS basically, plus
Okay.
from our odometry.
I see. And then the second question also, when you simulate the observations, so you once you have the 3D observation, you kind of tell or like quote teleport to some locations around your initial point, like the point that you actually have, right?
Yeah.
And then you see if you know the kind of parameters, you know which 3D points actually visible in your camera image, right?
Exactly, and then because it's not like a perfect, not perfect when like there is a hole somewhere, like you see here in the images, we basically interpolate, and the interpolation isn't good enough to.
Okay,
so
train. For the color, you just pick whatever you get. I guess your 3D observation also contains information about the pixel color.
Exactly. It also contains information about the color.
Okay, so so I guess in this case you don't really care about like how the pixel color should slightly change when you change the viewpoint then.
Yeah, we don't care about this. We assume there is no illumination change. But you actually ask a very good question regarding future work. For this approach, this assumption is fine. We also looked mainly at lane stable driving.
Yeah.
But it obviously becomes much more challenging once you want to do things like such as in-paint other vehicles, to do also multi-agent interactions.
Okay.
So from my viewpoint, that's like the next very challenging step to do. But yeah, for here, we just assume the color is the same. And because as you have seen, like it's only if you're on the road, you only slightly change your viewpoint. So the deformations even, they are relatively small, and the color changes that you would observe if you would be actually driving and recording would also be relatively small.
Okay, got it. Okay, thank you.
Okay, yeah, so basically here you actually can see the actual driving of the vehicle. This vehicle is driving autonomously on our Devon's test site, and the test never seen this particular data set except for in the simulated environment. So on the quantitative side, or let's say,
I actually had one also small question of clarification. So is it a requirement, like, do you expect the model to generalize to environments that it hasn't seen in the simulator, or is it really a prerequisite that you have collected the data for a specific location and trained the model in the synthetic version of that environment?
It's a very, very good question, Liam. So you remember probably the Devon's map. We have trained it only on the outer loop, but also used the inner roads for evaluation. So it does not have to be the very, very same environment, but it at least assumes a certain similarity. I think it also can generalize from highway to Devon's. But let's say the weather would be completely different. We would have completely snow-covered roads. Then it would not immediately generalize, at least not with the amount of data that we use. So one direction that is for us interesting to look at is to see how can we generalize if weather changes. What would we have to do to properly generalize for changing appearance conditions?
Okay, but 100% of the training is going on in the simulator.
Exactly.
Yeah, okay, got it.
So all the training was in the simulator.
It's just a question of which data you've synthesized into the simulator. Yeah. Okay.
Absolutely. Yeah, exactly. And I mean, at some point, what also gets interesting is, of course, how can you use real world data to not just synthesize slightly different viewpoints, but to also synthesize complete cities or synthesize like a complete street network so that you can generate more interesting scenarios or any handcrafted scenarios you could imagine. So that's as I understand, still an interesting open problem that we're also interested in looking at. I guess the general message in this slide is basically these other approaches with the same amount of data have just a much harder time to generalize. So we compared it to domain or adaptation or to some sort of variance of domain randomization, sorry, and also to simply augmenting the views by using a richer set of input views. And these other approaches, if you use massively more data, will also start performing better and better. But for the same amount of data you needed that we used for building the simulator, you obtain much earlier robustness on the driving task. So even for us, of course, end-to-end driving is interesting as a basic research question because it shows the nice interactions between control and the use of neural networks. But even if you're interested in other aspects of driving, such as perception, these type of Sorry? Was there a question? Okay, I heard a noise, sorry. So yeah, even if you're interested in some other research questions in perception, these type of simulators can simulate relatively rich appearance conditions or different viewpoints. So you could also use them to test out other parts of your driving stack and not necessarily just a neural network control module. And they also allow to do like robustness tests. So here we did some recovery experiments, and of course, because the simulator allowed for having different viewpoints and synthesizing these viewpoints, the car could recover from positions that were very far off from what it has seen in the data set, Okay, another problem that we were looking at, that is still for the driving task considered unsolved and very hard, and I cannot promise you the solution today, is the prediction problem. What we know quite well, like from past research on SLAM, is how to use maps and how to leverage maps. And one idea that we were looking at is leveraging maps for the trajectory prediction task. Let me quickly motivate it a little bit. So if you look at an average inner city intersection, in some sense, every intersection is different. So if the building that you see on the top is a school, then it's very likely that at this particular intersection, kids might run over the street, not watching the traffic lights. Also, depending on where the other streets are going and how long they are, how many pedestrians are typically around at this intersection, the average speeds in this area may be very different, and the typical trajectories may be very different. So we were interested in taking this inspiration and this observation and using it for creating a predictor. Before I will talk about what we did, I want to briefly look at how modern trajectory prediction approaches were. One of the first first very popular neural network based prediction approaches were social LSTM and social GAN. And what these approaches typically do is they use some sort of recurrent neural net for each trajectory and model the trajectory. And additionally, in order to incorporate some sort of social knowledge or social understanding, there is usually some sort of pooling module. In social LSTM, this pooling module basically allowed one LSTM node to look into the hidden state of the other nodes, basically incorporating the intuition that one pedestrian can guess the intention of the pedestrians around him. In social GAN, the pooling module was an MLP, but the basic idea was the same, to basically trying to guess the potential behavior of the pedestrians around you. More recent approaches use much more complex neural networks. The two emerging themes are, first of all, the use of graph neural networks for the prediction task and using graphs to model some sort of interactions between the pedestrians. And the second is to use some sort of attention module, either on the graph or to incorporate some sort of context information. And by context information, what they usually mean, it's another recent predictor, is either some sort of map, or often enough, it's a top-down view on the environment. So just some top-down photo that shows where pedestrians are and how they move. And we looked a little bit at what these networks do and how they work, and to get some inspiration. And what was very interesting for us were actually the ablation studies that these approaches did. So I think this is the ablation study for this social VecDat paper. I think they renamed it to A2GNN. The interesting parts here are the last 4 columns. The column that is denoted as T is simply the network that uses only the trajectory data. The next 2 additionally use context data. And the last one is the full approach that uses context data and a kinematic constraint. So the kinematic constraint is part of the neural network that constrains the prediction such that it is kinematically realistic. And there is some very interesting observation. So the first observation is that context is very important. You have to incorporate it in the right way, but it is extremely important. So once you add context, in this case, you need the attention module for adding context to work. The context information actually helps a lot to get the prediction right. And in this particular case, the context information is literally a top-down view of an annotated map. So the context information is something that the typical self-driving car company would already have. And once you add a kinematic constraint, what is also an interesting observation was that the kinematic constraint particularly helps for the distant future. So if you look, for example, at the first scene for a 5-second prediction, the kinematic constraint drastically reduces the average error and the final position error. So by simply adding such very small parts of like classical model knowledge into your neural network, you can actually help the neural network training a lot. And there is much more of this flavor coming out now in terms of prediction. So in the work that I'm presenting today, we mainly focused on the context problem. What is interesting to us is that state-of-the-art approaches did one of 3 things. Either they had no context modeling at all, and just looked at the trajectories, which, as we have seen, has been quite bad, or they just used some sort of image-based context models, or they used some handcrafted features or map-based context models. So the idea that we had was, can we actually learn the context model instead of simply providing something annotated? So can we allow the network to learn what is relevant for the prediction task on its own, where we only provide some sort of loose supervision on these context models. So we can use some sort of auxiliary tasks that involve the image. We can use the trajectories themselves, but ultimately, instead of feeding in for the prediction, feeding in an image, we just feed in this learned context map that is trained together with the network. And in this particular work, what we ended up doing, we basically had a predictor that was based on social GAN. And we integrated this idea with the social GAN predictor. So the top part that you see is just a modified social GAN version, and the part of social GAN that processes the trajectory just received an additional input, which was the local snippet of the context map. And this during training time, this context map was also trained. And it was trained by receiving information from the trajectories during backpropagation, but we also trained it by forcing it to predict how the image might look like, and adding some sort of regularization to make the map also work on areas where we haven't seen any pedestrian. So the cool thing about this is basically we now allow the neural network to learn context-specific information that is actually relevant for the prediction task. We started this work a while ago, so the evaluation was still based on the classical data sets. I think these days we would use some more, like ETH and UCY. We generated some sort of static top-down reference images that we used for training the context map. And what is different to older approaches is we didn't use different locations for training and testing. A lot of the neural network prediction approaches, particularly the earlier ones, make the following argument. They say, we test in one part of the environment and we generalize in another part of the environment. And we test for, we train in one part and we test in another part of the environment to see how good we generalize. But in reality, a vehicle traverses the same environment very often. So ideally, we would allow some sort of overfitting to a specific environment in a controlled way. And that's exactly what this context map idea does. So in order to test how good this works, what we basically did was we test on the same location, but we test a different time slice, simply to see how good is it encoded. Oh, I see there are some more questions. Sorry, I overlooked those. Please go ahead.
Florian, go ahead.
Sure. I wanted to ask, how is the context map represented, or like what's the format?
Mm-hmm. So the context map is just a tensor that has roughly the same size as the input image. It can be downscaled by a certain factor, but it's a tensor, and the number of map features is basically the third dimension of the tensor. So it's literally a 3D tensor. And in the forward pass, we cut out the slices of the tensor that correspond to the trajectory points that we are looking at. We look always at a patch around a trajectory point. So actually our forward pass was a little bit slow back when we designed it. I think these days, if I would design it again, I would use some sort of attention module rather than always cutting out parts of this tensor. But even with this approach, as you will see in the results, it worked quite well.
And sorry, you're cutting out part of the tensor, so as to like focus on that as opposed to the trajectory itself, like focus on the surrounding area.
On the area surrounding the trajectory, including the points of the trajectory. So during the forward pass, not the entire tensor is passed to the predictor, but only those parts that on which we want to predict.
Gotcha. Okay, thanks.
There was also a question by Ray.
Ray, go ahead.
Yeah. So how are trajectories represented? Is it like a sequence of observations? Like
yes, trajectories are just basically a vector of XY points for like a certain number of time steps.
Okay, and you just like input all of them at once.
Yeah, but we use a recurrent neural network. So
I see.
Yeah.
Okay, got it.
Okay. Yeah, and then basically the error metrics that we use are AD and FD, as everyone uses. So the average error and the error at the final position. It's actually not very good metrics, because most of the time these metrics, particularly when you walk straight, they will even look good with a linear predictor. So in practice, I think there is a lot of questions about what should be future metrics for trajectory prediction.
I had a follow-up question to Ray's question. So you assume like a fixed frame of reference here, a fixed world frame that's like a static overhead view that defines a fixed world frame. Is that correct?
Exactly. Another way, by the way, to do it, because here we had like these data sets that are just based on static trackers. So it's always the same frame of reference. But if you have actually an actual autonomous vehicle and you're interested in how things move relative to the vehicle, you can use the base frame of the vehicle as your reference frame. But these data sets, ETH and UCY, it's just some camera hanging around and filming people. Yeah, and we did also some loose annotations. It was Guy's and my drawing style, so they don't look pretty, but they are on purpose not covering everything. Instead, the argument that we make was, by having only some annotations, we allow the network to learn meaningful predictors even in areas that we have not annotated. So partial labeling is sufficient to actually learn successful prediction. And what we have seen in our case is that actually adding this context information made a huge difference. It's kind of is in line with what we observed with the other predictor that I have shown, social vector. The one thing that at first surprised us is that we sometimes perform better without the pooling module. But then when I looked at more recent SGAN results, they had similar situations. So actually building these pooling modules in the right way is a big challenge. And I think they were the reason why graph neural networks became so popular, because they actually model these interactions quite well. Okay, I think we have a little bit more time for my final topic that I want to briefly mention. It's geometric uncertainty modeling. There, I was not only motivated by driving. In the driving use case, we also have ambiguity. If our data looks like this, point clouds, we might not know in which directions the pedestrians here are going. But by observing them over a longer period of time, we might figure it out. But if we build autonomous systems indoors, estimating orientations of objects becomes actually quite hard, particularly if these objects involve some sort of symmetries. State-of-the-art approaches have a very hard time of dealing with such approaches. So one thing I worked in my PhD, in my PhD thesis, was directional statistics and dealing with symmetries. Back then, it was just very theoretical work, but it seems now to come very handy, because what if we ask our perception system to estimate the orientation of objects that look like a ball, a coffee cup, or some sort of pipe? The orientation of these objects has no obvious solution, because they have some sort of rotation symmetries. So one question we were interested in is, can we model these rotation symmetries in a principled way? And for this, we used approaches that are based on directional statistics. There were actually only very few works that use directional statistics. For example, for initializing post-graph optimization, for hyperspherical variational autoencoders, and for von Mises-based estimation of circular quantities. In our case, we were interested in estimating orientations, because in robotics, that's like the quantity that we usually look at. If we want to deal with objects and register objects, we're interested in orientations, and we want to do this using Quaternions. I think in this round, I don't need to introduce Quaternions in detail. The one thing that is important here is, if we want to use Quaternions and to model uncertainties over Quaternions, we ideally would like to have a probability distribution that accounts for the fact that the quaternion Q and minus Q represent the same orientation. So the idea that we had was combining neural network-based orientation prediction with probability distribution that just does exactly that. The probability distribution that we use is the Bingham distribution. At first, it looks exactly like a Gaussian. Its main difference to the Gaussian is that it is defined on the sphere. So the 2D version of it is simply a circular distribution that has two poles. The 3D version is a spherical distribution, and the 4D version is hard to visualize, but represents orientations. But the fact that this distribution has two poles is exactly what we want for quaternions, because Q and minus Q represent the same orientation. We would want to have every value Q and minus Q to have the same density in this distribution. What makes using this distribution so difficult is this normalization constant. Because it is defined on a sphere, this normalization constant is not the same as in the case of a Gaussian. So it's actually a hypergeometric function of matrix argument that is somewhat hard to compute. And I will talk about that in a minute, how we solved it. The contribution of this work that we presented at ICLR was basically similar to doing probabilistic deep learnings with Gaussians, where you predict a mean and variance. But instead of predicting mean and variance, we predict the parameters of a Bingham distribution, which is the parameter M and Z. M can be roughly thought of as the mean of the Bingham, and Z is roughly like the variance parameter. It's a little bit simplified, but for the intuition, it helps. And as I said, the problem is that we have here this normalization constant, and this normalization constant is annoying to deal with. So instead of computing a complicated function in every forward pass, we simply create a lookup table and interpolate through this lookup table. Sorry. The nice thing about this interpolation is that it can be done in a fully differentiable way. So you can build an RBF or most other interpolators such that they can be part of a neural network graph. The idea of using lookup tables for the Bingham distribution is actually not new, but simply placing a lookup table and an interpolator in your differentiable computation graph is one of the contributions of this work, and allows using the Bingham distribution for orientation prediction. And here you see the full pipeline. So you can input an image or some other type of data. It predicts the Bingham parameter, matrices and vectors. And ultimately, these can be used for evaluating the Bingham density that just operates on quaternions. We tried it on, first of all, on some very precise data sets where we tested with label noise. And as an error metric, we used the geometric counterpart to mean the angle, to mean square error. So in that case, we we simply defined what we call the expected absolute angular deviation, and its sample counterpart, the mean absolute angular deviation. And what we want in our evaluations is these to be similar to what we observe in the data. So here you see basically in a relatively precise data set, the target pose and the predicted pose by our network, including the uncertainty predicted by our network. And once we add labels, you can see that our network is actually pretty precise at predicting the label noise. So we want these quantities that show the label noise, and the first line we basically want to be close to the other two lines. One of them is the label noise that we added, and the other two is basically the one that our network predicted. In the very left case, we reached the limit of our lookup table. So there it is not possible because we didn't generate one that was large enough. But otherwise, we are very close to the observed uncertainty. Because it is very easy with very precise data, we tried this as well on data that is harder to predict because it contains actual rotational symmetries. And here you can see nicely how the network captures this uncertainty. When looking from the top, it's actually not having a hard time to predict it correctly because this tooth in the top is kind of revealing. But as we go more and more to the side, the network gets much more uncertain, but is correct about predicting this uncertainty properly. It still gets it somewhat right because neural networks are really good at detecting patterns. So it looks here even at the winding pattern, and this winding pattern is enough to still be somewhat good, but it becomes much more uncertain and is able to predict this uncertainty in a right way. Okay, I mean, we had some more evaluation in the different regimes, high and low uncertainty regimes. High uncertainty is when we stop the training earlier, simply to look how the prediction was. Low uncertainty, we trained a little bit longer. And the difference between the observed error, which is MAD and TAD, was in all cases relatively small, except for when we reach the limits of the lookup table, of course. So the nice thing is we were able to properly predict uncertain orientations, even for objects that are rotationally symmetric, with like a very high uncertainty, where actually the network itself would fail in the prediction, but our uncertainty prediction would correctly say how that it failed and would correctly assess this problem.
I have just a point of precision. So for those objects that have high rotational uncertainty, what does your label look like?
Mm-hmm. The ground truth label is still their true orientation.
So even if there is high rotational symmetry, you have to pick
exactly
something to be the label.
Actually, all these objects in the TLS data set, I don't like it anymore. There are better data sets by now. They are all not perfectly rotation symmetric. Only from some views, they are perfectly rotation symmetric, but not from all views.
Okay.
So therefore, there is always a ground truth label that gives you the perfect orientation.
Okay.
Thus this label was always true, but if you look from these directions where they have like perfect symmetry, your network basically starts telling you, okay, I don't know anymore which one it is. And that's actually exactly what we want. We want, like here in the second line, the prediction of the network failed completely, but the predicted uncertainty told us, okay, the network doesn't know what's going on. So we want to be able in uncertainty prediction to know when it fails. I want to do advertisement for two more related works. So since we published this paper, there were two, at least two, there are actually more, who did something very similar in spirit. It was an RSS paper by Perry Trukin. The second one is at CVPR. The second paper actually also did use the Bingham distribution. And I want to give them credit because they had the idea independent of us. They were only slightly later to publish, but they deserve the credit no less. And their idea there was very similar. And they also had evaluations on some more data sets. So it's also, if you're interested in this, worth taking a look at. Okay, so that's it. Thanks so much for your attention. I want to give credit to a lot of people who worked with me on this and on many other papers. And I look forward to your questions if you have more questions.
I had a question. It might be dumb.
All questions are good. There is no dumb question.
So now we've seen a few of these works operating on SO3 and kind of exploiting properties of the group, of the SO3 group. What about SE3? Can we do something similar? Or
it's actually, yeah, if this is a dumb question, then the dumb ones are the best ones. So for SE3, there are several interesting problems. I think one of the interesting problem generally is like how to represent dependency structure between orientation and position. And there are different views on it. Like sometimes you know the location very precise, but you don't know the orientation at all. But sometimes it's like, if it's like from the ego viewpoint and you do motion estimation, then not knowing the orientation completely destroys your knowledge of the position. Because if you don't know in which direction you're going, your odometry system will not help you. You might be like everywhere. You only know the distance that you went. So it's actually like if you want, there are a lot of approaches that model position and orientation, but there is no unifying approach yet that basically in a principled way can capture both types of uncertainties, like both of these types.
Right.
And account for it in a like geometric principled way. There is some cool work by Luca Carlone that in some shows when you can couple the estimation problem of position and orientation by first estimating the orientation and then doing the position estimate given the orientation.
Yeah, because it becomes linear.
Yeah, exactly. I also worked a little bit on it in the 2D case using basically dual quaternions, but so we have a similar distribution as the Bingham for dual quaternions in the 2D case, but deriving the same in the 3D case becomes much harder because you have to consider some algebraic constraints that make like the derivation of the distribution hard.
I think Florian has a question. Go for it.
Yeah, so first of all, thank you so much for the talk. It was really cool, especially at the end, the symmetric distribution, like modeling rotational symmetries as such. So I really find this like elegant and neat. I have a question from the about the very beginning, where you spoke about the ground penetrating LiDAR, where I didn't know yet I could ask questions like right away.
It's a radar though. It's not a LiDAR.
Oh, sorry, ground penetrating.
Yeah,
ground penetrating radar. Two questions. How robust is this to, like, so you showed this in isolation, like on this like clear intersection versus snowy intersection, but how robust do you think this is to like inner city noise? So let's say if there's I don't know, if there's construction work going on anywhere or like buildings going partially underground, could your radar like reflect off of other buildings or something like this, like garages and stuff? Question part number one. Question number two is, do you think compared to the like more and more available and cheaper LiDAR and depth sensors, that this is a thing that is that's going to become more widespread in the future?
I mean, I think Liam and I were both, to answer the last question first, we're both very excited about this sensor. Of course, ours is a prototype, so prototypes are super expensive. I don't think, though, that this prototype contains anything that needs to be expensive. In fact, radar is the sensor that automotive companies know much better than they do know sensors such as cameras and LiDARs. They have been using radar for a while, and there is no reason why this particular type of radar should be different. To answer your first question, what the system does is it looks directly under the ground, under the car. So what happens on the side is not as important. But once you're in the city, if you look directly under the ground, you might see a lot of reflections that are not just stones, but that might be, for example, from water pipes or whatever. My understanding is that these actually do more help than harm because they help you make your map more robust by adding additional features. But this I'm saying guessing into the blue because we haven't tried it in inner city roads.
Okay, thanks. And sorry, if I may add a quick follow-up question.
Yeah.
How was that system trained? Like, where did you get the data from to compare the scans from that you're getting, or the data from that you're getting from the radar? I
mean, this system was old-fashioned, so there was no training at all. We had we pre-recorded a data set, and in order to get ground truth, we used a differential GPS system, which gives us centimeter level precision.
But effectively, that thing, like what it can do really well is localize relative to some other time that you drove past.
Exactly.
So if you have an expert driver that collects data, then it would be able to sort of localize relative to that.
Yeah.
So in a sense, you don't need like necessarily to have centimeter precision ground truth location necessarily. You just need to localize relative to what somebody did before and assume that that was the right thing.
Yeah, exactly. And the maps that we recorded beforehand, they are somewhat precisely geolocated.
Did anyone, so like, I actually didn't look at that paper to be honest, but so like other limitations that struck me at the time were actually like reconciling that data into a consistent map, like doing SLAM, underground SLAM. Did anyone ever think about that, or maybe it's just...
we would love to do it, Leo. When I come to Canada, we can write some proposals on that. It's just currently we have still the prototype that we were given from Lincoln Labs, and it's a little bit...
So there is somebody that I know of at U of T who is working on this.
Yeah, I also know.
Okay.
I think we know the same.
Yeah.
But for them, my understanding is it's currently on the back burner because it was also a university-made device. There is a company that is selling a device, GSSI.
Yeah.
And I think it might be at some point worth just buying their device.
I got a quote from them. I can share it with you.
Did you find it, if I may ask, did you find it expensive, not expensive?
I'm going to just pause the live stream.